Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay. So this is the lecture number 11 of condensed matter physics, in which I'm going to discuss one-dimensional diatomic lattice vibration. Okay, and also, guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, and also I would request you to share. This detail to your to your to your friends who are studying in MSc or who are preparing for the physics examinations, okay, so that they can also get the benefit. Okay, okay guys, so let's get started. So this is the lecture number 11th of condensed matter physics. So we are studying one-dimensional diatomic lattice. Okay, one-dimensional one-dimensional diatomic lattice. Okay, one-dimensional diatomic lattice vibration or one-dimensional diatomic lattice. Okay, so I'll make this diagram in the figure. Okay, so this is, I have already explained one-dimensional monoatomic diatomic lattice vibration, guys. So you can check my previous lecture for this. Okay. Okay, so this is the one-dimensional diatomic lattice. Okay, this is, these are mass m1. Okay, this is mass m2. Okay, these are diatomic molecules. One-dimensional diatomic lattice. Okay, so this has mass m1, mass m2, m1, m2, m1, m2. Okay, so these atoms seems that they are attached with spring. Okay, of spring constant k, and then they vibrate in their mean position. Okay, so this is the one-dimensional diatomic lattice. Okay, and atoms are arranged in this way. Okay, and the spring constant is c for them. Okay, So for one-dimensional diatomic lattice, I'm going to write the dispersion relation. Okay, dispersion relation. Before that, let me check whether I'm audible or not. Okay, then I'll proceed further. Dispersion relation. Yes, I'm audible. So I'm going to proceed further. Okay, so dispersion relation for one-dimensional diatomic lattice is omega square equal to C into C is the spring constant. Okay, C into 1 upon m1 square plus 1 upon m2 square. Okay, so here m2 is greater than m1. Okay, mass of m2 is greater than m1. Okay, so diatomic lattice, we can take example of NaCl, right? This is diatomic lattice. Okay guys, just give me 1 minute. Okay, okay guys, so there's some issue, but it's okay, I'll proceed. Okay, so this is dispersion relation. Okay, dispersion relation, this is C into 1 upon m square plus 1 upon m1 square plus 1 upon m2 square, and then plus minus root 1 upon m1 plus 1 upon m2 whole square minus 4 sine square Ka by 2, this is the dispersion relation. Okay, Ka by 2 upon m1 m2. Okay, so this is the very important formula guys. Okay, you need to note down and solve questions, okay, using this formula, questions related to this formula. Okay, so this is the dispersion relation of one-dimensional diatomic lattice. Vibration is omega square equal to C 1 upon m1 square plus 1 upon m2 square plus minus root 1 upon m1 square plus 1 upon m2 square, root 1 upon C is also there, right? Okay, so C into 1 upon m1 m1 plus 1 upon m2, not square. Okay, 1 upon m1 plus 1 upon m2 into plus minus C root 1 upon m1 plus 1 upon m2 whole square minus 4 sine square K by 2 upon m1 plus m2. Okay, so this is the okay, so this is the dispersion relation. Okay, where omega is the frequency, angular frequency. Okay, and this one. Okay guys, just give me 1 second. Okay guys, thank you. Okay, so let's get started. Okay, so this is the very important formula. This is the dispersion relation, okay, for one dimensional diatomic lattice. Next we are going, so here you can see these values are omega square equal to c into 1 upon m plus 1 upon m 1 upon m1 plus 1 upon m2 plus minus c root 1 upon m1 plus m2 whole square 1 upon m1 plus 1 upon m2 whole square minus sin square k by 2 upon m1 plus m2, right? So this is, so here you can see there are two sign plus minus, right? So plus sign plus v sign is for optical branches, okay, plus sign is for optical branches, optical branch, plus sign is for optical branch or electromagnetic wave, okay, and minus sign, that is minus sign is for acoustical branch, okay, acoustical branch, acoustical branch, that is sound wave, for sound wave, okay. So the, so minus plus sign is for optical branch and minus sign is for acoustical branch, okay. So now we are going to study different cases, okay. So case number 1, at low frequency or large wavelength, at low frequency oblique large wavelength, okay. So this we can say this is equation number 1, okay, equation number 1. So at low frequency or large wavelength, this is the case number first, okay. So lambda is lambda is going to lambda is tending to infinity, okay. That is the large value of wavelength or low frequency. So it means we know, right, this is, it means k is going to be 0, since we know wave vector k is 2 pi by lambda, and also we know nu is c by lambda. Nu decreases means c by lambda increases, right? So from here value of k is 0, right? So it means sin ka by 2, this value is going to be 0, right? So if this value is 0, so this part is going to be 0, then the dispersion relation is going to be, or this is for acoustical branch, so the optical branch we are talking about, okay. So optical branch we are talking about means this for plus sign, okay. So omega square value is going to be, omega square value is going to be c into 1 upon m1 plus 1 upon m2, right, this value. And for optical branch we'll take only plus sign, right? So plus c root sin, this value is going to be 0, guys, sin k by 2 sin 0, right? So this is going to be 1 upon m1 plus 1 upon m2 whole square minus 0, right? So then the omega, and because we are talking about optical branch, so we'll denote omega by omega square plus, because we are considering plus sign only, okay. Because for optical branch we'll take plus sign, for acoustical branch we'll take minus sign, okay. So omega plus square is going to be c into 1 upon m1 plus 1 upon m2 plus this root value is going to be 1 upon m1 plus 1 upon m2, right? So 1 upon, this is c also there, okay, c is also there, okay. So this is going to be c into 1 upon m1 plus 1 upon m2. So So this is going to be, so these will get added, right? So 2c upon m1 plus 2c upon m2. Okay, this is omega plus square. So this implies omega plus value is going to be for optical branch. This is going to be root 2c is common, 1 upon m1 plus 1 upon. Okay, so this is the value of omega plus at low frequency. We are talking about optical branch. Okay, important formula. Well, and this is at k equal to 0, right? This is the omega plus. Now at low frequency, if we talk about high frequency, this is the low frequency and large wavelength, right? Now case 2 is going to be case 2 at high frequency. At high frequency, of oblique low wavelength. Okay, so in that case, high frequency means k is going to be high. Okay, because we know k is proportional to frequency nu, right? K is high, that means k is greater than 1. Okay, and here we know that m2 is greater than m1, right? This I have already mentioned earlier. Okay, so this is high, right? And the value of k is greater than 1. So this means sine k by 2 value, that is maximum value, is going to be almost equal to 1. The maximum value of sine is 1, right? So this value is going to be 1 maximum, right? So in that case, omega plus square is going to be this formula, right? Or c into this one, okay, right? So this is going to be c into 1 upon m1 plus 1 upon m2, okay, plus c root 1 upon m1 plus 1 upon m2 whole square minus 4 sin square k value is 1, right, upon m1 m2, or we can write one value 4 upon m1 m2. So this value is going to be, if you open it, 1 upon m1 square plus 1 upon m2 square plus 2 m1 m2, and this is minus 2 m2. So this is going to be 1 upon m1 plus 1 upon m2, 1 upon m1 square plus 1 upon m2 square minus 2 m1 m2, means 1 upon m1 minus 1 upon m2 whole square it is going to be, right? So this is omega plus square is going to be at high frequency, c into 1 upon m1 plus 1 upon m2 plus c, and this value is going to be root 1 upon m1 minus 1 upon m2 whole square, because if you open it, right, we are going to get this value. Okay, this value. Right? So now omega plus at high frequency is going to be omega plus square is going to be this one, c into 1 upon m1 plus 1 upon m2, okay, and this value is going to be plus c 1 upon m1 minus 1 upon m2, right, because 1 upon 1, this is 1 upon m1 minus 1 upon m2 whole square. Root will be removed and this will be the value. Now from here, this will get cancelled with this, right? So omega plus square is value is going to be 2c upon m1, 2c upon m1. So that implies omega plus at high frequency value is going to be root 2c upon m1, right? So from here we can write At higher frequency, that implies at higher frequency, omega, angular frequency, that is omega depends on lighter mass. You can see only m1 it is dependent. Okay, lighter mass means small mass. Okay, lighter mass. So this is in optical branch we are talking about. Optical branch. Okay, so this is at higher. So we have studied different cases for optical branch. Okay, and we've got this value. Okay, these values are important. Omega plus is this for higher frequency, and omega plus for at low frequency. Okay, next guys, next is for acoustical branch. Okay, this is optical branch that we have studied, right? Optical branch. This is the optical branch, guys. Okay, I can write here optical branch. Optical branch. Next is acoustical branch. Acoustical branch. Okay, acoustical branch means negative sign. Okay, minus b. Okay, so acoustical branch, the now we'll study different cases. Okay, so case 1, that is at low frequency, oblique higher wavelength, at low frequency oblique higher wavelength. Okay, so low frequency means higher wave lambda tends to infinity, that implies value of k is 0, since lambda equal to 2 pi by k equal to 2 pi by lambda. Okay, wave vector. Okay, so now if this is the case, sin k by 2 value is going to be 0, right? So acoustical branch we are going to take negative sign, right? So this is then will denoted by omega minus square. Okay, omega minus square is going to be c into 1 upon the value in equation 1. I have written the value of omega, right? So that is m1 plus m2, 1 upon m1 plus m2, and now we'll take minus sign. Okay, this one. Acoustical means minus sign, this one. For optical we have taken plus sign, and for acoustical we have taken minus sign. Okay, so this is c root 1 upon m1 minus 1 upon m2 whole square, minus sign 0 is 0, right? This is 0. So omega minus square is going to be this one, c into 1 upon m1 plus 1 upon m2. This is going to be, this is plus, guys. Okay, 1 plus. So to open it, so this is going to be minus c one upon m1 plus 1 upon m2. This is whole square and root will be removed, right? So this is the value. Now from here, omega minus square value is going to be, this will get cancelled, so this is going to be Mm. So this you can see these are going to get cancelled. Okay, same value. So this omega 0 is going to be 0. This will get cancelled with this, right? So this value is 0. Okay, so for at lower frequency of in acoustical branch, the omega value is 0 or omega minus is 0. Okay, now we'll study case 2. Case 2 for higher frequency. Okay, higher frequency oblique low wavelength. Okay, lower wavelength. So in this case, k is high, right? K is high. That means k greater equal to 1, right? And it means sine Ka by 2 is going to be equal to 1 because k value is large, so maximum value of sine is 1, right? K is large, very large, right? That's why sine maximum value of sine can be 1. Okay, that is the maximum value. So sine Ka by 2 is almost equal to 1. Right. So here then the omega minus square value is going to be, that is for acoustical branch, right? C into 1 upon m1 plus 1 upon m2, okay, minus C root 1 upon m1 plus 1 upon m2 whole square minus 4 sine square value is 1, right? 1 square upon m1 m2. Okay, so omega minus square value is going to be C 1 upon m1 plus 1 upon m2 1 upon m2 1 upon m2 minus C. This value, this you can see this is 4 m1 m2, right? If you open it, this is this and this will get cancelled, right? So this is going to be root 1 upon m1 minus 1 upon m2 whole square. Okay, if you open it, we have this value is going to be this. Okay, so now omega minus square is going to be omega minus square is going to be C into 1 upon m1 plus 1 upon m2, and this is, will open it, right? So this is going to be minus C 1 upon m1 minus 1 upon m2. If we open it, this will get cancelled with this. Okay, so this is going to be 2C. My apologies, this will cancel with this, right? So 2C upon m2. Okay, omega minus square. So it means omega minus value is going to be root 2C upon, right, for high frequency. Here you can see that implies in acoustical branch, in acoustical branch, frequency depends on heavier mass. In optical branch we have seen frequency depends on lighter mass, right? So in acoustical branch frequency, because m2, right, m2 is greater than m1, right? So m2 is greater than m1. I have already mentioned that here. Okay, so in acoustical branch frequency depends on heavier mass, this implies, right? Well, now I will draw a graph. Okay, that is versus that is wave vector versus the angular frequency. Okay, very important graph for exam purpose. Okay, so I'm going to draw it. Okay, this is omega, and this is k, omega versus k. Okay, so this is like this, okay, and this is like this. This one, and this is going to be like this. Okay, this is going to be this one. Okay, so this value is this we have got value of pi by a. Okay, right, this is at minus pi by a. Okay, and this is the this is acoustical branch, lower branch. Okay, acoustical branch. Okay, this is optical branch. This is optical branch. Okay, this is omega, and this value at this is root 2 c upon m2. Okay, for acoustical branch, this value, and this value is root 2 c upon m1 for optical branch, higher branch. Okay, and this is forbidden energy gap. Okay, forbidden energy gap, forbidden energy gap. Okay, this is optical branch. Optical branch, that is omega plus. Okay, this is acoustical branch, that is omega minus. Okay, and value of omega is root 2c into 1 upon m1 plus 1 upon m2. Okay, this is root, guys. Okay, okay, so this value is, these are straight lines, guys, or not looking, but these are straight lines. So this is root 2c upon m2, and this is root 2c upon m1. Okay, this is the forbidden energy gap. This is optical branch. Okay, omega plus acoustical branch. Okay, and this is between pi by a to minus pi by a to plus pi by a. Okay, this the omega value. This omega value is, I can write here, this value is omega equal to root 2c into 1 upon m1 plus 1 upon m2. Okay, root 2c into 1 upon m1 plus 1 upon m2. Very important graph. Okay, you should know this. Okay, this is forbidden energy gap, this is optical branch, and this value is root 2c upon m1, lighter mass, and this is root 2c upon m2. Okay, well, so this is the graph. Next is very important, this is the band gap or bandwidth. Okay, band gap oblique bandwidth, bandwidth. Okay, band gap oblique bandwidth. This is important, and that is W equal to bandwidth or band gap, which is denoted by W, that is root 2c upon m1 minus root 2c upon m2, right? And we know m2 is greater than m1, right? So this is important formula. So this is, you need to note down and memorize it. So it is W equal to root 2c upon m1 minus root 2c upon m2. This is the band gap or bandwidth, right? So there is one question which is asked in GATE and which is based on this formula, okay, which I am going to solve now. So question is, which is asked in GATE, okay, GATE. So question is, NaCl, that is sodium chloride, okay, NaCl, the band, you need to find out the bandwidth of NaCl or band gap of NaCl is denoted by Bw1, okay, and NaBr, okay, NaBr, that is sodium bromide, okay, and its band gap is denoted by Bw2, okay, Bw2, right? So now you need to find, options are given, you need to find Bw1 and Bw2, okay, and you need to find the relation between them, okay. So first is Bw1, bandwidth of W1 equal to bandwidth of W2, okay. Option B is bandwidth of W1 greater equal to bandwidth of W2, okay. Option C is bandwidth of W1 less equal to bandwidth of W2, and option D is none of the above, okay, none of these, okay. So this is the question. We need to find out bandwidth of NaCl and bandwidth of this, and then we need to compare which one is greater or are they equal, right? And we will use this formula, guys, okay, important formula, band gap and bandwidth. Well, so I'm going to solve it. So first of all, you need to know something, guys, okay. For NaCl, let mass of Na is m, chlorine is m1, okay, and for NaBr, mass of sodium is m, right, and B is, and Br is, suppose this is m2. And now we know the atomic mass of bromine, Br, is almost 80, and atomic mass of chlorine, Cl, is 35, okay, and atomic mass of sodium, that is Na, is almost 22. This we must know, guys, for solving this question, okay. So from this clearly m2 is greater than m1, right, because chlorine mass is m1, right, which is greater than m2. It's a bromine, right? Now next, so now we'll find Bw1 first. Bw1 equal to, there's a formula, root 2c upon m minus root 2c upon m1, right, in this case, right. So here also you need to know this one. In this case, m1 is greater than m, guys, okay, m1 is greater because sodium mass is atomic mass is 22, m1 is greater, and here m2 is greater than, because m is 80, for bromium the atomic mass is 80, right, and sodium 22, right. So this one, so we'll put the value to root 2c upon m value is this one, m minus root 2c m1, the same value, right. Now we'll find Bw2 is root 2c upon m minus root 2c upon m2. Here m1 is greater than m, and here m2 is greater than m, right? So now we'll find the bandwidth. Bandwidth means that is this one. So now we'll find W, this one, delta, no, bandwidth of W1 minus bandwidth of W1 minus bandwidth of W2. Okay, so that is going to be, we'll write this one, root 2c upon m, root 2c upon m minus root 2c upon m1, root 2c upon m1, root 2c upon m1 minus this value, root 2c upon m1, root 2c upon m1 minus plus this one, root 2c upon m2, root 2c upon m2, right? This will get cancelled, guys. Okay, so this is going to be root 2c upon m1 minus, this is minus root 2c upon m1 and root 2c upon m2. So you can see m2 is greater than m1, right? m2 is 80 and m1 is 17, right? So means this is plus, guys. Okay, this is plus. So if so this is going to give, this is greater value, so this is going to give negative value, means bw1 minus bw2 is negative. So if we subtracted bw1 from bw2 from b1, this is giving negative value. This means clearly bw1 is less than bw2. So which option is matching, guys? Let's see. Option C is matching. bw1 is less than bw2. bw2 is greater, right? This is how we find out the bandwidth of these different atoms. Okay, very important formula. Next question, guys. Next question is asked in CSIR net, December 2018. But before that, I'm going to tell you the trick, which is important trick, guys. You need to know this trick. Okay, so you can easily solve many questions if you know this trick. Okay, so trick is here you need to understand P is an effective, guys. Okay, effective number of atom, that is P. Okay, so now this is 1D, okay, this is 2D, and this is 3D. Okay, so number of branches, yeah, number of branches, number of branches. Okay, so first I can write here number of branches, number of branches. Okay, number of branches. Number of branches. Okay, this is 1D. Okay, so if you talk about acoustical branch, okay, acoustical for number of branches in 1D is 1, number of branches in 2D is 2, number of branches in 3D is 3. That is very simple, so you can easily know. But optical number of branches in 1D is P minus 1, guys. P is the effective number of atom. Okay, I'll solve question, then it will clear your doubt. P minus 1, okay, for optical branch. And for optical branch in 2D, number of optical branches or number of optical mode is going to be 2P minus 2. Okay, and for 3D, number of in 3D, number of optical branches or number of optical modes are going to be 3P minus 3. This is a trick you need to note down, guys. Very important. Okay, you can easily solve question. This is trick. Okay, this is trick. Now on the basis of this trick, I'm going to solve one question, very good question. Okay, So acoustical branches are same. 1D there is one acoustical branch. In 2D there are two acoustical branch. In 3D there are three acoustical branch. But in optical branch there is a trick that is for getting in 1D. You must know the N effective. If you know the N effective, then in 1D it is going to be 1p minus 1. In 2D it is going to be 2p minus 2, and in 3D it is going to be 3p minus 3. Okay. Okay. So now question I'm going to solve. This is asked in CSIR net December 2018. Okay, 2018. So question is B8TiO3. Okay, B8TiO3, that is barium titanate. Yeah, barium titanate. Just give me 1 second. Okay, just give me 1 second. I'm checking. Okay, it's barium titanate. Okay, barium titanate. It's barium titanate. So this is barium titanate, TiO3. Okay, barium titanate, and you need to find the number of, in barium titanate you need to find the number of optical branches. Barium titanate, my apology, it's barium titanate. You need to find the number of optical branches. Okay, number of optical branches you need to find out. Okay, and it's a barium titanate crystal structure is given, guys. Okay, I'm making that crystal structure, and you need to find out the number of optical branches. Okay, so it's a barium titanate. It's a 3D structure, right? 3D crystal. So this one, this is one atomic, this is this one. These are the corner atoms. Okay, 8 corner atom, and one atom is here, one atom is here, one atom, and one atom is here, guys. One is here. Okay, so this is the structure given, guys, and this is the structure of barium titanate. Okay, BaTiO3. This is given, and it's 2018 question, guys. Okay, so now you need to find out the number of optical branches, right? So there is a trick, guys. First we will find N effective. Okay, that is P, right? That is going to be, I have already told formula in my previous lecture, you can check it. So this is going to be 1 upon 8 into 8 corner, right? Corner atoms, plus 1 by 2 into face atom. Face atom are 6 atom are there, right? In the face center of the face, right? 6 atom, and there is one atom, this is at center, right? So this is Ni, right? This is 1. Okay, so this is going to be 8 at 1 plus 3 plus 1. So N effective is 5, guys. So you need to know this formula. N effective equal to this one, N by corner atom by 8 plus 1 by 2 face atom plus Ni. This is center atom, right? Face atom and center atom. I'm writing face by F. Okay, face atom. Okay, this you need to know. have already explained in my previous lecture, so I would request you watch that. So this is the so number of optical branches are 5, guys. Okay, 5. So now there's a trick. It's a 3D crystal, and we know there is a trick. So for getting number of optical branches for 3D, 3p minus 1, simple. So that is 3. So number of optical branches, number of optical branches, that is 3p minus 3, and that is going to be 3 into 5, means this is, because n effective is 5, right? 3p minus 3 minus 5 minus 3, 315, 5 is 15 minus 3, that is 12. So which option is matching, guys? Okay, options are given here. Okay, I forgot to write. Options are option A 5, option B 12, option C 13, and option D 6. Okay, so option B is matching, right? This is the answer. Okay, simple question, right? So this is the one, and I have already explained how to get n effective. Okay, and so if you talk about cubic crystal, then n by 8, right? C by 8, corner atom by 8, because there are 8 corners, right? Plus 1 by 2 face atom, F I have written, plus Ni, that is center atom, right? So that's why this one. Okay, guys. So okay, before ending the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, and also I would request the students, please share this with your friends so that they can also watch the classes at free of charges, right? And they can also be benefited for it.